What if I told you that everything you see around you, this chair, your phone, even you, isn't made of tiny point-like particles, but of something much, much weirder? What if the fundamental building blocks of our universe are actually tiny, vibrating strings of energy? This isn't science fiction. This is the core idea of one of the most mind-bending theories in all of physics: string theory. Let's rewind a bit. For centuries, scientists have been on a quest to find the ultimate stuff that makes up everything. We started with atoms, then we discovered they were made of even smaller things: protons, neutrons, and electrons. We kept digging and found that protons and neutrons are made of quarks. For a long time, we thought these quarks and electrons were the end of the road, fundamental, indivisible points. This collection of particles and the forces that govern them is called the Standard Model. And it's incredibly successful. It explains almost every experiment we've ever done. Almost. But there's a huge problem. The Standard Model has a gaping hole in it. It describes 3 of the 4 fundamental forces of nature: electromagnetism, and the strong and weak nuclear forces. But it completely leaves out the most familiar force of all: gravity. Our best theory of gravity is Einstein's general relativity, which describes gravity as the curvature of space-time caused by mass and energy. The problem is, general relativity and the Standard Model just don't play well together. They operate in different realms and speak different mathematical languages. Trying to combine them is like trying to mix oil and water. It's a mess. At the tiny scales where quantum mechanics reigns, gravity goes haywire, and the math breaks down, spitting out nonsensical infinities. This is the biggest puzzle in modern physics. This is where string theory waltzes in, offering a breathtakingly elegant solution. It says, what if you've been looking at it all wrong? Instead of point-like particles, imagine that at the heart of every quark and every electron is a tiny, one-dimensional, vibrating loop of energy, a string. Just like a violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings can vibrate in different patterns. And here's the beautiful part. Each different vibrational pattern corresponds to a different particle. One pattern of vibration makes the string appear to us as an electron. Another pattern makes it look like a photon, the particle of light, and another, a quark. It's an incredible symphony of vibrating strings creating all the matter and forces we see in the universe. It's as if the cosmos is a grand orchestra, and the laws of physics are the harmonies produced by these vibrating strings. So, what about that pesky gravity problem? Well, string theory predicts that one particular vibrational pattern of a string should produce a particle with the exact properties of the graviton, the hypothetical particle that carries the gravitational force. In other words, in string theory, gravity isn't an afterthought. It's a necessary and natural part of the framework. It emerges from the same fundamental principle as everything else. For the first time, we have a theory that can potentially unite the world of the very small, quantum mechanics, with the world of the very large, general relativity. It's a candidate for a theory of everything. But hold on, because this is where things get even stranger. For the mathematics of string theory to work, it requires something extraordinary: extra dimensions of space. We are familiar with 3 spatial dimensions: length, width, and height, plus 1 dimension of time. String theory, however, requires at least 10 spatial dimensions plus time for a total of 11 dimensions. So where are these other dimensions? Why can't we see them? The leading idea is that these extra dimensions are compactified. Imagine a tightrope walker. From far away, the rope looks like a one-dimensional line. You can only move forward or backward. But if you were a tiny ant on that rope, you would see it has another dimension. You could walk around its circumference. In the same way, these extra dimensions proposed by string theory could be curled up into incredibly tiny, complex shapes, so small that we are completely unaware of their existence in our everyday lives. They are woven into the very fabric of spacetime at a scale far smaller than an atom. These curled-up shapes, called Calabi-Yau manifolds, are incredibly complex, and the specific shape of these hidden dimensions would determine the vibrational patterns of the strings, and thus, the very laws of physics in our universe. This opens up another mind-blowing possibility: the multiverse. The theory allows for a vast number of different ways these extra dimensions could be folded. Each different configuration could create a different universe with its own unique set of physical laws. Our universe, with its specific constants that allow for stars, planets, and life to exist, might be just one of a near infinite number of bubble universes in a much larger cosmic landscape. Now, it's crucial to be honest about the status of string theory. As beautiful and powerful as it is, it's still a work in progress and faces major challenges. The biggest one is that we have no direct experimental evidence for it. The strings themselves are thought to be so unimaginably small, far smaller than anything we can currently probe with our most powerful particle accelerators, like the Large Hadron Collider. And predicting testable phenomena has been notoriously difficult. Critics point out that without testable predictions, string theory risks becoming more a branch of philosophy or mathematics than physics. Furthermore, it's not just one theory. It's a collection of different versions, 5 main ones to be exact, that all seem to be different theories. But in the 1990s, a breakthrough known as M-theory was proposed, which suggests that these 5 string theories are actually just different glimpses of a single, deeper, 11-dimensional theory. It's like 5 people describing an elephant in the dark. One feels the trunk, another the leg, and they all describe something different, but they are all describing the same underlying animal. So, is string theory the answer? Is reality a cosmic symphony of vibrating strings? We don't know for sure. It could be the most profound insight into the nature of reality ever conceived, or it could be a beautiful mathematical detour. But its pursuit has given us incredible new tools and ideas in both physics and math. It pushes the boundaries of human imagination, forcing us to ask the deepest questions about the cosmos and our place in it. It's a testament to our relentless curiosity to understand the true nature of everything. What do you think? Is this a crazy idea, or the key to unlocking the universe? Let me know your thoughts in the comments below. And if you enjoyed this journey into the bizarre and beautiful world of physics, don't forget to like this video and subscribe for more mind-blowing space explanations. Thanks for watching, and keep looking up.